Hello everyone. Thank you for tuning into the Oracle IAM Insights session today. My name is Mike Campbell and I am an analyst in the Identity and Access Management group with a primary focus on OAM. Today I will be covering how to use the recently released automation tools to configure an OAM environment in a Kubernetes cluster. While this session is focused on OAM, the same general procedures can be used to configure OUD, OIG, and the microservices as well. We have a full agenda today, so we will be moving through these topics pretty quickly. More details can be found within the Enterprise Deployment Guide for Kubernetes clusters, as well as the Oracle Fusion Middleware GitHub site, which will be referenced shortly. Today we will cover the advantages and obstacles to running OAM in a Kubernetes cluster and provide two different installation options. The majority of the session will focus on the automation scripts themselves, providing some details about how they work, what steps still require manual configuration, a sample walkthrough of using the scripts to build an OAM environment in a Kubernetes cluster running in OCI. When first learning about setting up a Kubernetes cluster to run OAM or any of the identity management products, it initially sounds like a lot of overhead to configure and maintain. However, once configured and running, there are several benefits to using the Kubernetes cluster environment, most notably. Number one, scalability. Traditional non-Kubernetes clusters rely on using the WebLogic commands pack and unpack to configure an additional node to an existing OAM cluster. However, with the OAM running in a Kubernetes cluster, it is very simple to scale up or scale down the number of managed servers. This is done by editing the Kubernetes domain and changing the number of replicas desired. Kubernetes will then automatically adjust the number of running managed servers to match the requested replica count. Secondly, high availability. Traditional non-Kubernetes clusters rely on external load balancers to route requests to an available OAM managed server. When using a Kubernetes cluster, that is handled internally within Kubernetes itself. Requests are routed to the Kubernetes services, and Kubernetes will then decide how to route the request internally. If a managed server is down, Kubernetes will detect that and route requests to other managed servers automatically. Monitoring. Kubernetes knows how many managed servers are expected to be running based on the Kubernetes domain definition. If for some reason the number of managed servers falls below that threshold, then Kubernetes will spin up additional OAM instances automatically, distributing the load across the available worker nodes. And finally, patching. Instead of using the traditional approach of downloading a stack patch from MOS and using OPatch to apply it to the OAM installation, one simply edits the Kubernetes domain definition to identify the OAM image to use. Kubernetes will then do a rolling restart of each managed server, bringing it up with the new image. However, there are a few obstacles to running IAM in a Kubernetes cluster. Generally speaking, this is the time and knowledge required to set up the Kubernetes cluster. This includes such things as creating and initializing the Kubernetes cluster by setting up the control node as well as the multiple worker nodes. Configuring a persistent volume, which is needed to store the WebLogic domain files and must be shared across all of the Kubernetes worker nodes. Running a lot of kubectl commands to create the Kubernetes namespace, secrets, and Kubernetes domain. Creating several YAML files to describe the desired state of the Kubernetes cluster. And creating port mappings to allow the end user to access the Kubernetes cluster and to route the request to an OAM managed server. As far as installation options go, Oracle provides two different options for installing OAM into a Kubernetes cluster. The Oracle Fusion Middleware GitHub site lists each identity and access product along with the required steps. This will result in a working configuration but with limited integration and connectivity. For example, once the OAM section is completed, there is no integration with OUD nor OIG. A Kubernetes ingress controller is created, but it is only accessible via the Kubernetes controller node or primary Kubernetes node, and only accessible outside the cluster if that node is publicly accessible. Integration and accessibility can be configured after the OAM installation is completed, but those steps must be completed manually. As such, most people would consider this type of environment better suited to a development model. The second option is to use the Enterprise Deployment Guide for Kubernetes clusters. The EDG contains the most complete documentation to configure and integrate all of the identity and access products, spanning 700 plus pages with hundreds of kubectl commands to execute during setup. The EDG covers references to firewalls, SSL, hardware configuration, Kubernetes, container runtime options, on-prem versus OCI installations, and much more. The EDG is the desired approach for a production environment, but can be overwhelming when getting started. Once the theory lesson has been completed, the EDG walks you through the configuration of the OCI infrastructure pieces that are common to all of the IAM products. Finally, there are individual chapters dedicated to the configuration of each IAM product. The number of commands to run and cross-references to other EDG sections make the EDG tedious and time-consuming to use and understand. Just the sheer number of objects to be created make it very easy to make typos and mistakes that are difficult to track down when trying to figure out what is causing problems once the installation is completed. In an attempt to simplify the configuration of a Kubernetes environment, a set of automation scripts were developed to configure and integrate each of the IAM products. These scripts are part of the Fusion middleware Kubernetes scripts that are downloaded from GitHub as part of the IAM Kubernetes setup process. They are documented in Chapter C of the EDG, which provides an overview of using the scripts. Some points of interest. A common response file is created which determines which products will be installed, configured, and integrated. When a failure occurs, the script stops at that point. The problem can be corrected and the script restarted again, and it will pick back up where the failed step. There is no need to do any cleanup before restarting the automation script. There is a prerequisite check that is done before any configuration is attempted. This ensures that the environment meets the minimum requirements needed to run successfully. Currently, the automation scripts are capable of configuring a Kubernetes Ingress Controller, OUD, OUD Services Manager, the WebLogic Operator, OAM, OIG, and the microservices Identity Role Intelligence and Advanced Authentication. To use the automation scripts are pretty straightforward. A response file needs to be created, which can be done manually, editing the file and setting the desired values, or by running the start_here.sh script, which will provide an interactive question and answer type interface to create the response file. Even if the interactive option is used, it is still acceptable to edit the resulting file manually and make any last-minute changes. Once the response file has been generated, it is a good practice to execute the standalone prerequisite check script to check connectivity to the container registry if you're using one, connectivity to load balancers, connectivity to the databases used for OAM and OIG schemas, access to the NFS servers, and so forth. I will note that the same prerequisite script is executed when the provisioning script is run as well, but it is often better to run the prerequisite check itself to check and fix for any problems up front. Once the prerequisite check completes successfully, the provisioning script can be executed. You can execute the main provision.sh script, which will in turn execute all the individual product scripts that are enabled in the response file, or you can execute the individual product scripts manually one by one as needed. In either case, the same automation scripts are executed to set up the IAM products defined in the response file. Here we can see a sample execution of the prerequisite check script, which shows the checks being made. Note that in this case, the Oracle Container Registry is being used instead of local images. And once the checks return a success, we can proceed with running the provisioning script. Chapter C of the EDG lists many steps that the automation scripts will complete for you during the integration of the various IAM products. However, it is important to note some of the things that the automation scripts are not designed to configure. The first 4 items in this list need to be done before the automation scripts are run. You need to set up the Kubernetes cluster and its dependencies, such as flannel networking. You need to install an Oracle database that is accessible from the Kubernetes worker nodes so that the RCU tool can create the OAM and OIG user schemas. You need to set up the HTTP servers, which will be used as a proxy between the outside world and the Kubernetes Ingress controller. And as referenced by the prerequisite checks, there are various load balancers required to be configured. Finally, if not using container registry to pull the container images from, then images must be manually downloaded onto each of the Kubernetes worker nodes. The remainder of the items in the list are to be done post-installation as business requirements dictate. These can be done by following the steps from the EDG. The next couple of slides show the output from the OAM portion of the automation script. This is the output one would get when executing provision underbar OAM.sh manually. The steps generally follow the order of the steps in the EDG. For OAM, this would be Chapter 15 of the EDG. Here you can see the creation of the Kubernetes namespace for OAM execution of RCU to create the OAM schemas, the creation of the Kubernetes secrets, the creation of the persistent volume on the NFS server, and the creation of the OAM Kubernetes domain. Continuing the automation script, we can see step 24 where OAM is integrated with OUD, and step 34 where the OHS virtual host configuration files are created and copied to the OHS servers. Once the provisioning is completed, a summary is presented showing how long each step took and an overall start to finish time. This execution took approximately 45 minutes to complete all the steps from Chapter 15 of the EDG. This is a significant time savings over manually running each of the 25 plus commands shown in the chapter. In addition to the time savings, there's little chance of skipping a step or making typos that would cause problems. While the automation scripts are great for configuring the various IAM products, they still rely on the fact that the underlying architecture has already been created before the script is run. For example, in an earlier slide we saw that when setting up a Kubernetes cluster in OCI, it requires the creation of 3 load balancers, 3 compute instances, an OKE cluster, 5 VCN subnets, 8 VCN security lists with approximately 60 ingress and ingress rules, a rack database, 17 NFS mounts, a DNS server, and several other items. All these are documented in Chapter 9 of the EDG, along with the commands needed to create these resources. Again, these are time-consuming to create and prone to errors if done manually. IAM support has created a bash script that will automate the creation of the underlying infrastructure pieces. This bash script uses the OCI command line tools to create these components without the need for any user interaction. Oracle KM Note 287.1808.1 contains a script named edgoci.sh that can create all the components from Chapter 9. This script is not officially supported and provided as on an as-is basis only. As such, the KM Note is not publicly available. To get a copy of the script, please open an SR with Oracle support for guidance on setting up and using the script. Once you have a copy of the edgoci.sh script, read the comments at the top for information about setting up and using the script. Since the script uses the OCI command line interface, it is required to have the OCI command installed on the machine where the script is being run. You will edit the edgoci.sh script and update the required variables described at the top of the file. Specifically, you need to provide full path to an SSH public and private key that will be used to make a secure connection to the Bastion host. Have created a compartment to contain all of the resources to be used in this Kubernetes cluster environment. Have created an OKE cluster from within the OCI console. Define the region name where the OCI resources will be created. Set the Linux image name to be used for the compute instances, and to set a password for the database that will be created. There are variables at the top of the edgoci.sh script to be updated with the above information. Once these variables are set, the script can be run with the expected output shown over the next couple of slides. Like the automation script, the edgoci.sh script creates the OCI resources in the same order they are presented in Chapter 9 of the EDG. Here you can see it's creating the Bastion host and its related resources, the web tier host, the NFS mounts, and the public load balancer. Once the edgoci.sh script completes, it provides a few pointers of additional information that will be needed. First, it provides the full SSH command to use to connect to the Bastion host. Next, it states that the initial rack database, called OAM PDB, is being created and will take a couple of hours to get to a running state. Once that pluggable database is available, you should run the provided OCI-DB command shown to create the OIG PDB pluggable database. Using both the edgoci.sh script to create the OCI infrastructure pieces and the EDG automation scripts to install, configure, and integrate the IAM products, the workflow would be something like the following. Create an SSH public and private key. Use the OCI console to create a new compartment for the OCI resources. Create an OKE cluster from the OCI console. Retrieve the OSID values of the OKE cluster and the VCN from the OCI console. Edit the edg.oci.sh script and modify the variables at the top of the script. Run the edg.oci.sh script to create the resources in Chapter 9 of the edg. Wait for the container database to become available. Create the automation script response file. Run the automation script prerequisite checks, and finally run the provisioning.sh script. Generally speaking, it will take 5 to 10 minutes for the manual steps, which are the first 4 items listed, roughly 30 minutes for the edg.oci.sh script to complete, about 2 hours for the OAM PDB database to become available, 5 minutes to add the OIG PDB pluggable database, 15 minutes or so to create the automation script response file, about 1 minute to execute the prerequisite checks, and 45 minutes to execute the automation script to integrate OUD, OAM, and OIG. Thus, the total setup, installation, and configuration time is around 4 hours from start to finish. As can be seen with this overview, the use of automation scripts greatly speeds up the time to set up an OAM Kubernetes cluster, taking hours instead of days, and is much less prone to error than manually configuring each piece. I thank you again for tuning in to today's Oracle Insights session. We look forward to seeing you in the next one.